My name is Joseph. So today we'll talk about my research project a bit. So basically, the main motivation behind our research project is to control the latency, is to improve latency in the network. So basically, what we're doing is there's an algorithm called AQM, so active queue management algorithm, which controls the queue length or the buffer size of routers in the network. So this allows us to prevent a phenomenon called buffer bloat. This is due, this phenomenon causes increased latency and variability, right, which we don't want. So that's why we want to use AQM algorithm. And there are various AQM algorithms, FQ-Codel, FQPI, Pi-Codel, but amongst all of those, we want to use L4S. So L4S is our main this thing because it's like low latency, low loss, scalable through. So L4S has two queues. One is the L4S queue, and the other is the classic queue. So when you are passing packets through this algorithm, it will filter them. It will classify them into L4S or classic. So if it's high priority, it goes into L4S. If it's not a high priority, it goes into the classic. So using a formula, it has a certain relationship. So the L4S and the classic queue. So there's something called as drop probability, which says like the probability of dropping this packet uh, is called drop probability. So what this formula says here is it says that PC is equal to PCL by K raised to 2. So it's controlling the, so it's saying, well, L4S has to be given more priority, but also it's also saying do not give too much higher priority to L4S. So basically, we are controlling the priority given to each queue using this relationship. K is called the coupling factor. Depending on how we want to do, we can change the coupling factor. And then we want to implement A3C. So we basically just using during our experiments, we collect all our data and we feed them into agents into the A3C model. So this is our network topology. We have four devices, two hosts, and two routers. And we have two scenarios. One is high bandwidth 10 Mbps. One is low bandwidth 1 Mbps. So this is our RTT graphs. These are some of our graphs. So what we can see here is FQ-Codel performs really bad in terms of RTT, but FQPI and L4S are better than FQ-Codel. Especially L4S performs the best in terms of RTT amongst all the other algorithms, and that is what we want. But when we look at throughput, so in terms of throughput, what we can see is FQ-Codel performs the best, and then comes FQPI and L4S. So in terms of throughput, L4S and FQPI are quite similar. There's no advantage to either of them, and which is not bad. We don't want L4S to perform any worse than the other algorithms. Uh, so this is what we have, and then once we feed all of our experimental data to our A3C, so we have four different. So considering we have like two routers and we have like two different flows in each routers, so we are collecting the data from each stream in both the routers. So we have total four streams. So we have four workers and we have four data files, and we are feeding them into the A3C model. And this is our reward graph. And what this reward graph basically says is our model is working properly, and we can see that the model is converging, and it does improve the performance of L4S. And this is what we basically want. So we can see a demo. So yeah, basically here it's already running. So you just run a script, and we can see, oh, so it's almost reaching 400. So it stops at 400. But then these are still going because it starts at different times. So we have four IPUF, three IPUF. Yeah. So we have four. So we have four IPUF three data streams, which starts at 0, 40, 80, and 120 seconds, and it each lasts for 400 seconds. So this is what we and and then we'll talk about this is our predicted and actual queue delay using our A3C. And what we can say that the predicted queue delay from our A3C model is a lot better. And I think I don't know if you're able to see this, but this is for agent worker 3. So we have for all three agents we have different. Yep. So this is all I have.